Yeah, thanks, John, for the very kind invitation to this nice meeting. Yes, I'm going to talk about this recent work that we've been doing in collaboration with the team at Yale, of Rocquencourt, Liang, and Michel especially. I'm, by the way, my name is not there, but I'm Mazyar Mirrahimi at INRIA. And so I'm in a superposition between INRIA and Yale. Essentially, I'm 4 months a year at Yale. And so this is part of the work I did through the last, some of the last stays there. And in collaboration with Zeki in particular, who's postdoc now with Michel Deboré, and who is doing the experiment on this theory that I'm going to present in this talk here. So he's going to be here next week, and I believe he's going to have a poster in the praxis meeting, where he's going to present some of the experimental results on this work. Okay, so here's an outline of the talk. Probably I won't have time to go through all these stuff that I've written here, so maybe I'm going to skip some of them. We'll see. And so I'm going to start by a very brief introduction to what are Schrödinger cat states and why are they interesting for quantum error correction. So what is the idea behind what we want to do here? I'm going to also present very briefly a couple of experiments that we've been doing at Yale on these ideas through the last 2 years, but I'm not going through them at all. It's just really giving somehow the direction of research that we are following. And then I'm going to go through these new ideas, new ideas in some sense, because they have been present in the literature in some ways before anyways, but we want to use some kind of non-standard dissipation for quantum harmonic oscillator. We want to engineer some kind of a non-standard dissipation for a harmonic oscillator, so that we have as a steady state subspace space of Schrödinger cat states that are of interest for us and that we want to use for quantum error correction. So we're going to use ideas are very similar to dissipation engineering or reservoir engineering in general, where the steady state subspace is not going to be a state, but it's going to be subspace, a manifold of states. We can talk about also decoherence-free subspaces. And we're going to use this decoherence-free subspace for encoding our quantum information. And I'm going to show how we're going to use these subspaces to do universal quantum commutation with some. What are essentially the other building blocks that we need to perform universal quantum computation with these Schrödinger cat states? And here we're gonna see some similar stuff to what we saw a couple of days ago on quantum xenodynamics in the talk given by Daniel. So I'm very happy that he gave this talk because it's gonna be probably you can see this part as an example of what he was presenting a couple of days ago. And finally, I'm gonna finish by the implementation schemes that we are following, and essentially some idea about the experiment that Zeki Lektas is running right now. So you're going to see that in the last part. So I would say that the interesting part probably for experimentalists is going to come at the end, pretty much. Okay, and I'm most probably not going to have time to talk about fault tolerance of these schemes. That's something we can discuss afterwards if you are interested. Okay, so what is a coherent state, or what's a Schrödinger cat state? Well, of course, you know for a quantum harmonic oscillator that these coherent states are the states which are probably the easiest to prepare in the lab. For example, in these microwave experiments within circuit QED regime, we can just apply a microwave pulse to put a coherent state inside a cavity. So we essentially, this coherent state will be represented by the state alpha, which in the basis of Fock states could be represented and as this, where here you see the Poissonian distribution of the Fock states, or in the IQ space or in the phase space of the quantum harmonic oscillator, it could be represented by Gaussian centered around alpha, the complex value alpha, with I and Q quadrature for phase space. And the phase here is defined relative to a local oscillator, for example, the generator of this pulse that we have been using to to put this coherent state inside a cavity or inside the harmonic oscillator. And so what are the Schrödinger cat states that are of interest to us here? Those are these Schrödinger cat states. So I also call them parity Schrödinger cat states. So state which is of the form superposition of alpha and minus alpha. Here I'm going to just be interested usually in the plus or minus sign, essentially. I'm not really interested in other phases for now. And so the interest of these states, which I'm going to represent by this symbol here, so cat alpha plus and cat alpha minus, are going to be the states that if you write down in the Fock spaces, you're going to see that you have only even parity Fock states or odd parity Fock states as a function of whether you have plus or minus sign there. You can also represent this in by the Wigner function in the phase space, and you're going to see that the difference is just that you have a positive fringe in the middle at center for plus sign for the even parity cat, and a negative fringe in the center if you have an odd parity cat. Okay. Okay. So what's the idea, and why are these states interesting for quantum error correction? So this is the idea that we essentially were developing a couple of years ago, so which was published last year. Essentially, we're interested in encoding and protecting quantum information on a single cavity mode. So instead of using a multi-qubit register as usual as standard codes, we're interested in using just a single cavity mode, a single harmonic oscillator to encode redundantly quantum information and to protect it against dominant noise channels. So what is the interesting, the main motivation behind it is just that we want to have a very hardware efficient, essentially quantum error correction protocol. We want to use minimal hardware possible to do this, and the minimal hardware is going to be pretty much what I have presented here within a CQED QED framework. It's really such kind of protocol could be considered as a minimal hardware needed. So you need a single high Q cavity mode, single high Q resonator, which is going to be used as a memory where we encode the information. We need a single qubit, but the qubit here is just going to provide some nonlinearity for our system, essentially. It's just going to be there to give us the controllability over our harmonic oscillator. It's not used to encode quantum information. It's really just used to give the controllability over our harmonic oscillator. And finally, we need also a low Q cavity mode and low Q harmonic oscillator to evacuate entropy or to do measurements, essentially. So that's pretty much the minimal hardware you could think of in a CQED QED experimental setup for doing some quantum error correction. And so that's what we want to use to do this. So what is the idea? The idea is just that we're going to use for logical 0 and 1 of quantum information these cat states. So for 0 logical, I'm going to use just the cat state alpha plus minus alpha, so which I can represent in the phase space with these two blobs with a plus sign in the middle. So this is the even parity cat state alpha plus minus alpha. And for 1L, I'm not going to use alpha minus minus alpha, but I'm going to use actually I alpha plus minus I alpha. So it's just another parity cat state, but along the other quadrature of the phase space. Okay. So why is this encoding interesting? Essentially, it allows us to protect our qubit against the dominant noise source in a QED setup, which is the photon loss channel, essentially the decay of photons. So how can I model this decay photon loss channel? Well, you can essentially a way of modeling it is through the quantum trajectories of the system, where you can see that, well, if you have weighted, let's say that initially you have some initial superposition of 0 and 1 logical, so some initial superposition of these two cat states, and so with coefficients C0 and C1, and then you wait for some time t, small t. So there is one of these possibilities could have happened during this time t. Either no photon has been lost during this time, so in that case, essentially you find out the same superposition C0 cat plus and plus C1 cat plus. The only difference is just that the blobs or the coherent components have shrinked a little bit. So they have shrinked with this exponential minus kappa t over 2. So because this is just the fact that even if you don't see any photon being lost, there is some information which you're gaining, which is just that most probably there is less photons inside the cavity. And so that's just the deterministic energy relaxation of coherent states inside the cavity. Now, what is the second possibility? That it's just that you have, during this time, you have had a single photon which is lost. In that case, well, you're still going to find the same the same components, alpha and minus alpha, and I alpha with exponential minus kappa t over 2. But the only thing which is going to happen is just that you're going to have the A operator applied, the annihilation operator applied to this state. And look, what is the application of the annihilation operator to this state? It's just alpha minus I alpha, and this one is going to give you I alpha minus I alpha. So if you look, it's just nothing other than saying that we have this plus sign which becomes minus sign, and there is an I coming out, and this plus sign becomes minus sign as well. So this is the state if you have had one photon loss. If you have two photon losses, the same thing is going to happen. You're going to jump back to the C plus with 2 times I, which is going to give you a minus sign. So this, with respect to that one, is like a phase flip, essentially. And then if you continue, you're going to have another jump. It's going to become minus with an I sign. And finally, after 4 losses, you're going to come back to the initial possibility. So essentially, you have just these 4 possibilities. And it's, yeah.
If your cavity is a little bit hot, and so it's putting photons in, does a very similar thing happen?
Well, it's no, it's becoming more complicated in this case, but I'm going to come. So let me come back to this question at the end, because anyway, this is not going to be exactly what you're going to need. But this is true. In general, a dagger, if you have an a dagger channel, what's going to go on is just that for large cat states, it's going to have a similar action as a channel. Okay. But for small cats, it's not the same. So it depends on the size of the cat, pretty much, how large alpha is. But in any case, I'm not going to need that. That's not going to be a problem. I'm going to go later. I'm going to show you actually a protocol which is protecting against all these decay channels, anyways. So okay. So this is one of the possibilities that is going to arrive as. So we're going to have one of these possibilities during this time. So this is nice because if you look, this state is the state which in the Fock basis basis is an even parity cat. But this state in odd is an odd parity cat. This is an even, this is odd, and this is even. So essentially, if you were able to keep track of the parity, photon number parity in the cavity, you were able to follow the jumps. Essentially, you were sure which encoding you were using in your quantum information. So you could erase essentially this this error, pretty much. That's the idea that which is behind all this. So essentially, the idea is that parity measurement is a jump indicator. So if you have a continuous parity measurement of the number of photons inside the cavity, and of course we need also to pump energy in a non-linear manner in our cat state. So essentially, you see that these blobs are going to shrink, and they're going to get they're going to continuously converge towards a vacuum, and eventually they're going to overlap, and the information is lost anyways. So you need also to come and essentially pump energy in a nonlinear manner inside this cavity state to bring them, to keep them at their initial energy. So if you have a way to do this parity measurement and this energy pumping, then you have a way to protect your quantum information. So in this paper, essentially we propose an autonomous scheme to do this without really doing any parity measurement even. So it's using just some chain of logical gates which transfers the entropy on an ancilla system and which evacuates its entropy and which also pumps the energy at the same time. Okay, so we have been, through the last 2 years, we have been trying to go towards this experimental realization of this protocol, so there has been some progress since then. So there was, the first step was to encode a qubit on such conducting cat states. So we followed, we had this theory proposal, using the strong dispersive coupling regime of a single qubit, a Transmon qubit, with a harmonic oscillator to do this. So, and so we did this experiment. And so essentially the nice property of the protocol that we had proposed was that the time of, essentially the idea was to encode a single qubit. We got a Transmon qubit. we transfer the superposition of the ground and excited state of a transform qubit on such kind of four-leg Schrödinger cat state, essentially. And so the nice property of this proposal was that the time of the protocol didn't depend on the size of the cat. And so it allowed us to make Schrödinger cats with very large size. Essentially, we could have Schrödinger cats up to 100 photons inside the cavity in this experiment. And then there is this newer experiment, recent experiment, which is the second step pretty much, which is continuous quantum non-demolition parity measurements of photon numbers inside the cavity. So this is an experiment which just was published a couple of weeks ago, I think, in Nature. And so essentially we have quite a good fidelity parity measurement for such cavity. And pretty much we think that just by putting these two bricks together, we should have at least a protected quantum memory in some sense. Well, protected probably with the properties of the encoding and parity meason that we have right now. The improvement is not going to be impressive. It's probably going to just be a factor of 2 or 3 at the best. But this is already not bad, because probably it's going to be the first quantum error correction scheme. Experiment quantum error correction scheme where we're going to see actually that some lifetime is improved actually, and we are not just correcting some errors that we are inducing ourselves, pretty much. So that's yeah.
So I didn't understand. So what measurement is? You say parity measurement, but you describe with like photon counting.
It's not a photon counting. It's okay. So the parity, Oh, you're talking about this?
Yeah.
No, this is just a discretization of the possibilities of errors. But it's just like any quantum error correction scheme where you need to do syndrome measurements. For example, for a 3-qubit Shor code, you use parity of the qubit 1 and 2, and parity of qubit 2 and 3, and continues to be able to follow the errors. And here, in this case, the syndrome that you need to measure continuously is the parity of number of photons inside the cavity. Okay, so that's. I'm not gonna talk about that because it's a whole. If you want, we can discuss how it is done.
It's different from just photon counting.
Yeah, of course. Because if you do photon number counting, of course you're gonna destroy the information here. Right. That's what you don't want to do that, of course. But however, in this talk, I'm gonna actually concentrate on doing quantum. So I'm using actually another protocol, which is quite different from the ones we had presented before. So this is a new direction we are following now. Where we use some engineered dissipation to essentially restrict our dynamics in the state of in this manifold of these two states. So essentially, we're not going to allow these blobs to shrink at all. For example, we're going to have some dissipation which keeps these blobs there, some nonlinear dissipation. With this, it keeps discordant components where they are, and it also corrects for dephasing channels. And so essentially, it really helps us to go beyond only the single photon decay channel. And we have also the possibility to do universal quantum computation. So okay. Well, okay. I should say maybe at this point that encoding quantum information in an oscillator is not a new idea. Of course, it's been already, there is a set of papers that you can see here. The list is not for sure complete, but people have thought about this before. What I should say is just that with these quantum superconducting circuits, we have some new perspectives. We have some new tools that could be really make this natural, this choice very natural. I believe you had a talk by Liang last week, which presented some of these essentially features of quantum superconducting circuits. I think he's going to give another talk next week, so that's probably going to become clear during his talk. But in general, you have properties such as long-lived coherence. So for 3D microwave cavities, we have now microwave cavities which can live up to 10 milliseconds. They have lifetimes of about 10 milliseconds, which is very nice. We have nonlinearities, which could be very large and which could be very well controlled. We can have a large spectrum of nonlinearities and with various Hamiltonians and with various strengths. So that's by just using various configurations of resistant junctions, essentially. That's a nice property that we have. We have also strong couplings, of course, and we have a flexibility in Hamiltonian design. But I think this is the most important message here, is that working with these oscillators is very natural, actually. It's with superconducting circuits, because everything is actually oscillator. So in a circuit QED scheme, transparent qubit is another harmonic oscillator, which is slightly more unharmonic, I would say, non-linear, than the usual harmonic oscillator. So everything is really harmonic oscillators. We are coupling harmonic oscillators with various degrees of unharmonicity together. And so it's very natural to just go back to work with harmonic oscillators instead of using a qubit, I would say, qubit restriction of a quantum harmonic oscillator. Okay, so let me just explain what is this dissipative process that can allow us to restrict our dynamics to such kind of Schrödinger-Cat state subspaces. Okay, so you know, of course, all of you know the case of a driven damped harmonic oscillator. If you have this LC oscillator, this quantum harmonic oscillator, which is driven by a generator, essentially, and which is dissipating, for example, dissipating to a transmission line, you can model this through such kind of Limblad equation, so with the decay operator, which is given by the annihilation operator, and you have such kind of ghost drive Hamiltonian that you see over here, epsilon being the complex amplitude of the drive. And so the steady state of such a system, of course, we know that it's a coherent state. Okay, so if we have a driven damped harmonic oscillator, what we're going to put inside the cavity is pretty much, we're going to finish by some coherent state of some amplitude, which depends on the amplitude of the drive and the decay of the cavity through this formula. Okay, so it's nice. It means that even though we have a decay, we are ending up with a pure state. No, the idea is just to essentially extend this. What happens now if you had some kind of interaction of your harmonic oscillator with its environment, such that you could lose not only one photon, but d photons at the same time to the bath. Or you could exchange with your drive also d photons at the same time. So you had a drive which is exchanging d photons at the same time with your system, or a bath which exchanges d photons at the same time with your system. Okay, so it's just a simple, theoretically simple extension of the previous case. What is going to happen is just that if you, for example, consider the case of d equal to 2, well, the steady states, you're going to have a degenerate space of the steady states, actually. So the steady states are going to be both plus alpha and minus alpha. They can be any superposition of plus alpha and minus alpha, with alpha being this. So you're not going to end up in the alpha state as before, but you're going to end up with a plus or minus. So there is a phase and precision here. And you can, any of these states, if you start from plus alpha minus infinity, plus alpha infinity, or minus alpha infinity, or any superposition of plus infinity and minus infinity, through this dynamics, you're going to stay there. So these, you could consider them as the coherence-free states of this dynamics. Okay, so and how about now if you consider instead of d equal to 2, d equal to 4, the steady states are going to be actually fourfold. The state space of the steady states is going to be four-dimensional. And those are going to be actually the states that I was interested in. So alpha, I alpha, minus I alpha, and minus I alpha. So all these states are going to be steady states of my dynamics, and any superposition of them is going to be a steady state of my dynamics. Okay. So okay, this is the idea. So the idea, when you see this, this gives us a possible choice of qubit. So for example, in the two-photon process, so in the case where d equal to 2, one can come and say that, well, I'm going to use this two-photon decay process, and I'm going to define my logical qubit as this. I'm going to call my minus z state, so the 0 logical of my qubit, or the 1 logical of my qubit, to be cat alpha minus, and the other logical state to be cat alpha plus, because these two states are orthogonal to each other, because those are different parity states, and they are those are stable states of this dynamics. Okay, and so the plus x, for example, and minus x, so states are becoming actually something similar to alpha and minus alpha. They're not going to be exactly alpha and minus alpha. The reason is just that this normalization that you have here is not precisely the same. It becomes the same only in the limit of large alphas. Okay? So it is normal that these are not exactly alpha and minus alpha because plus x and minus x should be orthogonal, whereas alpha and minus alpha are not exactly orthogonal, but they become pretty much orthogonal in the limit of large alphas. Okay, so this is a natural choice of qubit basis for a 2-photon process. And we have also a natural choice of qubit basis in a 4-photon process, if in the case t equals to 4. So in that case, you could come and take for the plus z and minus z states what I call C alpha 0 mode 4 and C alpha 2 mode 4 states. So how do you understand this? So the plus z state is going to be the addition of all alpha, minus alpha, I alpha, and minus I alpha states, which in the Folk basis can be written as just superposition of Folk states which are 0 modulo 4. And the minus z state is C alpha 2 mod 4, which is the superposition alpha plus minus alpha, minus alpha, minus I alpha, minus I alpha, which modulo 4 represents the states which are 2 modulo 4. So these two states are still orthogonal to each other, and they are also stable states of my 4-photon pumping scheme. And so still here, plus x and minus x become actually equivalent to C plus alpha and C I alpha plus, which are not exactly orthogonal to each other again. So this is approximately here. But these two are exactly orthogonal. Okay? Okay, so once I have said this, let me just first show why is this, for example, interesting. Why does it protect, if I have such kind of encoding on my of my qubit through this driven dissipative process, why do I have protection against dephasing, photon dephasing? So essentially, photon dephasing is fluctuation of my phase space. So essentially, fluctuations of my frequency of the harmonic oscillator, which could lead to some kind of decay, which could be represented by a decay operator of the form A dagger A and not A. Essentially, this is a dephasing channel for a harmonic oscillator. Okay, so how can we understand the effect of this in presence of this driven dissipative process? Okay, first of all, such kind of decay cannot change the number of photons modulo 2 or modulo 4. Because you see, A dagger A commutes with each Folk state. So if you start from an initial superposition of C0 mode 4 and C2 mode 4, the populations of this manifold and this state and this state cannot change because of this decay channel, because it commutes with them, with the parities, with modulo 4s. Number photon modulo 4. So population of plus C and minus C remains necessarily constant. Okay, so it means that it cannot induce any bit flip error. When the population of plus C and minus C remains constant in a logical qubit, you know that you cannot have any bit flip error. However, you can have a phase flip error. Okay, so it can induce some kind of phase flip. And so what I'm gonna try to explain very rapidly is just that this phase flip rate is actually exponentially suppressed with the size of the cat. Okay, so essentially what you see here is the rate of phase flip divided by rate of dephasing. So essentially you have some dephasing rate, and so you have the phase flip rate on the effective qubit. Okay, so initially they are similar to each other. They are one, actually. This is 1/2 of the kappa phi. And what you see is that if I now consider the size of my, I consider larger and larger size cat, so alpha is the size of my cat, essentially the amplitude of my coherent state. What I'm going to see is that very rapidly, exponentially, I'm going to have this rate of phase flip decay towards 0. This is the same thing for the 4-photon process. It happens. You still have an exponential decay. It only happens a bit later, so it's actually a square root of 2 times later. I'm going to explain that in a okay. So how to understand this exponential suppression of the phase flip rate? Okay, so this could be understood by such kind of plots here. So what you see here is that, so here I'm considering, for example, case of alpha squared equals to 2. So I have a cat size of square root of 2, essentially. Alpha equals to square root of 2, and which means mean photon number inside the cat equals to 2. And what I look at is just that each point in this plot means that if I start at a coherent state at this point, where I'm going to converge to, actually. Okay, so maybe I'll have probably to just do some math here. So how to understand a phase flip? This is for the for the two photon damping process, for two photon driven damp process. So we know that the zero logical, we said that the zero logical is the state alpha plus minus alpha, and one logical is the state alpha minus alpha. So how to understand a phase flip? A phase flip is the state which brings the state plus x to the state minus x. So what is the state plus x? It means the sum of the two should be brought to the difference of the two. The sum of the two is alpha, and the difference is minus alpha. So it's a process which should bring the state alpha to minus alpha. And essentially, this cannot happen because this two-photon driven damp process can be understood as in a classical picture, could be understood as a double potential well. Essentially, you have two extremely stable points, which are alpha and minus alpha. So if you start in all this region of your IQ space, you're definitely going to converge toward minus alpha. And if you start in all this region of you're definitely going to converge toward alpha. Okay, so that means that this phenomenon of jump from alpha to minus alpha cannot happen. And this becomes, you see, with the size of the cat, this region becomes more and more straight. So there is just a narrow line where you can have a jump, actually. So this is what we mean when by this suppression of phase flip in exponential manner. So however, in this slide, we have also some more information. This is, as I said, the population of the coherent states alpha and minus alpha. What you see here is the purity of the final state. Because it's not true that if you start from any place, you're going to go towards a pure superposition of alpha and minus alpha. What can happen is just that actually, if you start along this line, you're going to actually converge to a mixture of alpha and minus alpha. It's a driven that. But there is a point which is interesting. This is the point in the center. If you you start from the vacuum. The vacuum is a pure even parity state. You start from an even parity state. You exchange only photons in pairs. In even numbers with your system. So the only possibility is that you end up with a given parity state. So it's for sure you're going to converge toward the only parity state, which is alpha plus minus alpha. So these states are going to converge toward a pure state. Okay. Now, this is one decay channel, which was the dephasing photon dephasing channel. No, the other decay channel, which is actually the more important one, the photon loss channel that I talked about before, what is going to induce? So as I said, this photon loss channel could be seen in two parts. There's the first part, which is a deterministic decay of energy. This part is going to be suppressed exponentially in the same manner as dephasing, because still these two points are stable points of your dynamics. So you cannot have the event of shrinking. Essentially, this shrinking cannot happen. So you're going to keep your coherent components where they were initially. However, the second process, which is a random jump of photons, so a random application of the annihilation operator, can happen. And applied on a cat alpha plus, it can bring you to cat alpha minus, or applying to cat alpha minus, it can bring you to cat alpha plus. So actually, the application for the two-photon process, you can translate essentially the photon loss channel to a bit flip channel. Okay. So we have a qubit. Actually, already in the two-photon process, we have a qubit which only sees a single decay channel, which is bit flip channel. It can never have phase flip channels. It only sees bit flip channels. This is quite nice already, because it means that if you wanted to do a code in a let's say usual way of doing it, you just need 3 qubits essentially to encode information. But however, what I'm going to say is that if you, instead of using two-photon process, you use a 4-photon process, then still what is going to happen is just that the application of A is going to bring you the zero logical, which is C alpha 0 mode 4, to C alpha 3 mode 4, okay? And the C alpha 2 mode 4 is going to be brought to C alpha 1 mode 4, essentially. And this is a nice property. It means that this is tractable now, because you can just measure parity continuously again. And you know that if you have had a jump, your new encoding is this basis. And if you have not had a jump, your encoding is still C0 mode 4 and C2 mode 4. So we have the tractability by parity measurements of our photon loss channel. So I can probably summarize what I have said till now as this. I have a two-photon driven down process, for which I can use a logical qubit basis given by C alpha plus and C alpha minus. In this process, the photon dephasing induces phase flip errors whose rate is exponentially suppressed by the cat size. Photon loss induces bit flip errors who are not corrected for, or not tractable, at least not in this form. However, for the 4-photon process, I have a logical qubit basis C alpha 0 mode 4 and C alpha 2 mode 4. The photon dephasing still induces phase flip errors whose rate is exponentially suppressed by the cat size. And the photon loss this time induces errors that are tractable by photon number parity measurements. Okay, so that gives you already a possibility of doing a quantum memory, having a quantum memory where we encode information and we keep the information there, essentially. Now I want to do universal quantum computation with this. Okay, so what I need to do is a set of universal gates. I need to do a set of universal gates on this encoded information. So what is the set I'm going to choose? I'm going to show how to do arbitrary rotations around x-axis of a single qubit. I'm going to show how to do 2-qubit entangling gates. And I'm going to show how to do a pi over 2 rotation around the z-axis of my qubit. And with these 3 gates, I have a universal quantum computer. And essentially, the idea is going to be based on quantum xenodynamics here. So that's how I'm going to do these gates, essentially. I'm going to have this driven damped process on, and I'm going to add some other dynamics, some other Hamiltonians to my system, which effectively will induce such kind of unitaries on my system. Okay, so let's see. I'm going to present everything on a 2-photon process. The 4-photon process, I'm going to just explain very rapidly afterwards how you can extend this 2-photon process to the 4-photon process. Theoretically, it's very simple. Experimentally, it's much more hard work, of course, but as you can imagine. Okay, so for the 2-photon process, okay, we want to do arbitrary rotations around the x-axis of a single qubit. As I said, my 0 logical and 1 logical are C alpha plus and C alpha minus. So what is the arbitrary rotation in these spaces around the x-axis? So an arbitrary rotation of angle theta around the x-axis could be written in general in this form. You have a cosine theta identity in these spaces, plus I sine theta sigma x in these spaces. Okay? That's what I want to do. So, okay, if you look at this unitary, what you see is that in order to, what is going on is just that we have a population transfer between odd and even parity states, because we need to go, if we start from odd, we need to go to even, and vice versa. And for sure, we know that this is not possible only by 2-photon processes. Okay, we had the 2-photon decay-driven dissipative process. We exchange only photons in pairs. So this is for sure. It's not possible to do this only with keeping exchanging photons in pairs, because we need to go from odd to even, or vice versa. So we need single photon exchanges with the system in some way. What is the simplest Hamiltonian that ensures single photon exchange with your system? It's just a drive. There's a resonant drive with your harmonic oscillator. If you apply so if you have this driven damped harmonic oscillator that with 2 photons at each time that I said, and you add only to this a single photon drive, that's exactly going to do this. I'm going to show this. Okay, how to understand this? This could be understood in the framework of the xenodynamics. So of course, I'm going to assume that this epsilon x is much smaller than the kappa 2 photon. So this is the restriction. So we have this dissipation process, which is the strongest rate, and we can do gates at rates which are smaller than this. Okay, so how to understand this? Essentially, if we start from the cat alpha plus, which means alpha plus minus alpha, alpha plus minus alpha, you can understand this. So this is important. Okay, I have maybe skipped this. You see that there is a phase difference between A plus A dagger, and here it's minus sign. So here I have minus, and here I have plus, and this is important. Okay. I mean, it's important in the sense that any phase would work. You should just not choose A minus A dagger. That's the only case which would not work actually. Okay. But okay, this is the best case actually. A plus A dagger and A squared A dagger. So how to understand this? So if you have this process, as I said, the state which you're going to stabilize is alpha plus minus alpha. Now, adding this drive, you can discretize this dynamics in this way. I apply first for a small amount of time this Hamiltonian. So I displace my system with some epsilon, I epsilon. So because of the phase that I have chosen here, I'm actually displacing in the orthogonal direction to my cat. So if I had my cat, which was alpha plus minus alpha, I'm displacing it in this direction. So these are fringes. I'm displacing this cat in this direction. This, of course, because of the displacement of a coherent state, is going to induce some relative phase between the two. And now I project again, because of this, I project again on the space of cat alpha plus and cat alpha minus. So which, if you do this, brings you to such kind of dynamics, which is exactly the dynamic I was looking for. It's a Rabi oscillation of between cat alpha plus and cat alpha minus. You can understand this in this picture. The way to understand this in this picture is just this. You have this cat state. You're trying to displace it upwards. So you're displacing pretty much everything upwards, the fringes and the cat. But you're projecting it back on the cat. So by projecting it back on the cat, essentially you're projecting this part on the coherent blocks on this part, but the fringes, they have rolled over. So the fringes have rotated. And so by changing these essentially fringes, you are doing this gate. That's the idea. So you could also understand this in the framework that was presented by Daniel. So it means that if you have this A plus A dagger Hamiltonian, you're projecting it on the space which is stabilized by the dissipation process, which could be seen as a measurement process essentially, which is cat alpha plus and cat alpha minus. And very simply, you can see that the projection over this of A plus A dagger is just sigma x. So it's just effectively the dynamic that we're gonna have. And so this is numerical simulations. So where I have chosen a cat state of moderate size, I would say, alpha equals 2. I have chosen this separation of time scales that I said. So this epsilon x needed to be smaller than kappa 2 photon. I have chosen the separation of 1/20 in my simulations. And this gives me a gate fidelity in excess of 99.5%. So which is what you see here. Essentially what you see is just population of cat alpha plus and population of cat alpha minus. I see some Rabi kind of oscillations. You see that eventually I'm going to lose some of the fidelity. This is because of essentially the fact that this Zeno approximation is a first order approximation. Of course, there is going to be second order effect, which is going to reduce effectively the fidelity of this decay. So you can improve this fidelity or this this decay time by making this separation of time scales larger and larger. Okay. Now how to do a 2-qubit entangling gate. I'm going to explain how to do a 2-qubit entangling gate. So I want to do some effective Hamiltonian of the form sigma x times sigma x. I want to produce effectively, so here you imagine that you have two of these cavities, which are both driven damped towards these cat spaces, and you want to do something equivalent to sigma x on them. Okay. So what does this mean? It means that I want to do signal photon exchanges between the two cavities. So what is the simplest Hamiltonian that does single photon exchanges between two cavities? It's just a beam splitter Hamiltonian. If you have the two cavities with two driven damped harmonic, two photon driven damped processes, and you add this Hamiltonian of a beam splitter with epsilon xx, which is still smaller than the kappa 2 photons, essentially decay times, you can do exactly the same math. So by projecting on the associated space, cat space of A1 of both cavity modes, you're going to see that this is actually effectively the sigma x Hamiltonian we were looking for. So I can do also numerical simulations of this essentially master equation here, and that's what you're going to see. So this is, you can see that starting from here I'm starting from the state, I think, cat alpha plus, cat alpha plus. And what I'm looking at is the population of the Bell states that you see over here, cat alpha plus, plus or minus I, cat alpha minus, cat alpha minus. And what I see is just that I'm going to entangle the two qubits, two logical qubits, essentially, with some fidelity in excess of 99%, still with the same kind of separation of time scales. Okay. And finally, so the last gate that I need to finish, to have a universal gate, is a pi over 2 rotation around the z-axis of a single qubit. And paradoxically, it's the hardest one, actually. Why is that the hardest one? It's just because of the same reason you have protection over dephasing, you cannot do yourself either the rotations around the z-axis. Okay, so that's a bad thing. I mean, you have a qubit which is protected against phase flip completely, but of course it makes it hard also to do operations on the z-axis itself. So okay, for now the only possibility that we have presented is to turn off the pumping during this time and to do something. And this something is just applying some Kerr Hamiltonian. Okay, so you turn off the pumping, you apply the Kerr Hamiltonian for some time, pi over 2 chi Kerr, and this is going to be exactly pi over 2 rotation around the z-axis. Okay, so this experiment of using these Kerr Hamiltonians were recently done also in Rocquencourt's group. So we believe that this is feasible. It's not necessarily very, but it's not as nice as the previous ones because you have during this time you don't have any protection against the dephasing channel, for example. However, so you can have protection against photon number, photon loss channel because you can keep measuring parity during this Kerr Hamiltonian, and everything is going to be fine for the photon loss channel. But the dephasing channel is not going to be protected during this time. However, it's not that important because if you have the Kerr strength, which is much stronger than the dephasing time, just turning on the pumping after the operation is going to correct for the phase error that you have accumulated during this time. Okay, so and this we believe is going to be the case in the general for all these circuit QED experiments that we're going to have. We can have Kerr strengths which are much larger than the dephasing rates. Okay, for the 4-photon process, everything is going to be exactly the same. You have just to replace every operator A with A squared. That's just this. Essentially, everywhere I said I want to exchange photons in single photons with my system, here I want to exchange photons in pairs with my system because I have everything modulo full, right? So the sigma x operation is going to become exchanging 2 photons with my system at the same time, so which could be done by a squeezing Hamiltonian instead of a drive. Of course, it's more difficult experimentally, but mathematically it's going to follow exactly the same manner. So it's just you replace every A by A squared, and you're going to have all these. You can perform all these operations. So in particular, this beam splitter Hamiltonian is going to become a beam splitter who exchanges 2 photons between the 2 modes at the same time. Okay. And the Z gate, however, is the simplest one. This is the simpler here because this, again, the Kerr Hamiltonian, the same Kerr Hamiltonian would work here for the 4-photon process and the 2-photon process. It's actually you will need actually less time for this one. You need pi over 8 chi Kerr instead of pi over 2 chi Kerr to perform pi over 2 rotation around the Z-axis. So here I'm summarizing this part. So what I've shown is that for the 2-photon process, I have a decay operator of A squared. I have a driving Hamiltonian of this form, A dagger squared minus A squared. I can do arbitrary rotations around the x-axis by just resonant drive, epsilon x, A dagger plus A. Pi over 2 rotation around the z-axis is ensured by a Kerr Hamiltonian, and the 2-qubit entangle is ensured by such kind of beam splitter Hamiltonian. In the 4-photon process, every A is replaced by a square, so you have decay operator which is A4, deriving Hamiltonian which is I epsilon 4 photon A dagger 4 minus A4. The arbitrary rotation is A dagger 2 plus A2, and the pi over 2 rotation is still the same, chi Kerr, A dagger A squared. And the 2-qubit entangling gate is such kind of weird, I would say, a beam splitter. Okay, so let me just now very briefly present the implementation scheme. So this is the experiment which is currently run in Michel Devore's group at Yale. So we are still sticking with this minimal hardware setup. So we have a memory, IQ cavity. We're going to have a Josephson junction. I'm not going to call it a qubit because no, I'm not going to use the qubit at all. It's just a nonlinearity there. I never use the qubit. I never excite the qubit mode. It's just a nonlinearity that I provide there. It's just a Josephson junction. And I have a readout cavity, which is low Q, which is there. So it is my setup. What I'm going to do is just that I'm going to apply two drives on my system. One drive, one very strong pump drive, whose frequency is given by 2 times frequency of the memory minus the frequency of the readout, and then a drive at the frequency of readout, a weak drive at the frequency of readout. This is very similar to parametric amplified JPA, for example. It's just that we have a mode at this frequency omega b. Okay, low Q mode at this frequency omega b. Oh, I'm sorry, he went. So how to understand? Okay, I want just to. Okay, maybe I can. Yeah, maybe I can come back later. So what I have is just that I'm going to use the coupling, which is provided through this Josephson junction. So this is, you have 2 cavities, a Josephson junction in tunnel, which is coupled with 2 of them. This Josephson junction is going to ensure a nonlinear coupling between readout and memory, which, using this pump drive, is going to ensure some effective Hamiltonian of the form A2B dagger plus A dagger B2. So it means that 2 photons of the memory are going to be exchanged by a single photon of the readout cavity and a photon of the pump. Actually, that's what's going to happen. That's a parametric process that's going to happen. Okay, and so this is essentially just the fact that if you look at the Hamiltonian of the Josephson junction, well, it can be written as a cosine. It can be written as a cosine, and so the cosine is the phase which is inside the cosine. It needs to be a superposition of the two harmonic oscillators, essentially. So you're going to have some coefficient, some C, A plus A1, AS for the storage, AS dagger, or I use A and B actually, A and CA, A and A dagger, plus some CB, B plus B dagger. And so in this cosine term, if you develop this cosine term up to the 4th order terms, so up to the 2nd order terms, it's just quadratic Hamiltonian. There's no nonlinear effect. If you develop the cosine up to the 4th order terms, and you take into account the effect of the pump, which is at frequency 2 omega A minus omega B, and you keep only the the resonating terms, what you're going to see is that you can have the processes where 2 photons of omega A, so 1 photon of omega B and 1 photon of omega pump can give you 2 photons of omega at frequency omega A, or vice versa. This could be also the other way. Okay? This is the parametric process that could happen because we have chosen omega P to be 2 omega A minus omega B. Okay. So, okay, you can write, and so what this is going to give you, if you write the effective Hamiltonian of this using some black box quantization, for example, schemes that have been developed recently, you can see that you have actually such kind of couplings between A and B mode. So you have this A squared B dagger term that I had that I'm interested in. And I have also, because of the drive at the frequency of the drive, I have also this driving Hamiltonian B plus B dagger. And then I have some other nonlinearity terms, so some Kerr effects, A dagger A squared, B dagger B squared, and some cross Kerr between the 2 cavities, A dagger A, B dagger B. These are all induced by the Josephson junction, which is in between. Okay, so you can have all these kind of nonlinear effects. But these are all that exist at this 4th order, up to this 4th order. Okay, so those are all the terms which you have to keep to up to the 4th order calculation. And what I'm going to assume is just that everything, pretty much everything, so epsilon B and this G2 photon is smaller, or much smaller than the decay rate of the readout cavity. So the readout cavity is the lowest, is the fastest system in Mazyar. And I can do adiabatic elimination of the mode B. So essentially what I am doing is just that I'm mediating the dissipation of the cavity A through two photons through the cavity B, where two photons of cavity A exchanged by a single photon of cavity B and which is lost afterwards. Or vice versa, a single photon which is given to the cavity mode B with this drive, with this resonant drive, can be transferred to two photons of the cavity A. So essentially, I'm engineering my dissipation in this manner to the environment. And this is going to actually effectively give me this dynamic that I was looking for with the parameters epsilon 2 photon and kappa 2 photon, which depends in this form on the parameters of my system, G2 photon and kappa 2 photon. Okay, so Zeki has fabricated this sample. So this is what it looks like. It's not actually the sample that Zeki is working on, but similar one. He's working on a similar one. So this is the storage cavity. This is the high Q cavity. This is the low Q cavity, so which is very coupled to a transmission line. And the Josephson junction sits in between the two. So it's a transmission line which with antennas in both cavities essentially, and which is a transmit qubit essentially there, but which is never excited. It's just there to provide a nonlinearity. And so the parameters here that he has obtained are just the storage cavity with some lifetime of 20 microseconds. Okay, so it's not the best cavity that you can obtain, but it's still not bad. The important figure of merit is actually the separation between the two time scales of the readout and the high Q cavity. And what he has obtained is very nice actually in this regard, because he had 25 nanoseconds for the readout cavity. So readout cavity, which is 1,000 times faster than the storage cavity. And the two photon strength, coupling strength, G2 photon that he obtains here is about 120 kilohertz, which gives us a kappa 2 photon, which is of the order of 1/20 microseconds. So it's very similar to kappa 1 photon. So we are not still where we want to be. We want essentially to have two photon procedures which are much faster than single photon procedures to be able to correct faster than decay happens, essentially. But we are not far. I mean, we have at least two photon processes which are at the same order as single photon processes. And essentially, he has been able to see actually cats appearing. So he starts from vacuum, and he turns on these two pumps, and he sees the cat appearing. And then because of the single photon process, it eventually decays out, and we lose it. Okay, so you're gonna see his poster, I think, next week here. No, so in order to finish, you can also do all these gates that I was talking about by such kind of architecture. So first of all, arbitrary rotation around x-axis is actually simple. You can just apply another drive at frequency of the cavity A, and that's gonna do arbitrary rotations around the x-axis of your qubit. Well, pi over 2 rotation is just turn off these pumps and wait because of this Kerr term that is there. You're gonna effectively have this pi over 2 rotation. And for the 2-qubit entangling gate, this is the architecture we are thinking of. We have this is one qubit, this is another qubit essentially. And so we couple the two storage cavities through another Josephson junction. And we apply now another pump whose frequency is the difference of the two cavities divided by 2. So it induces, through the same parametric process, an effective beam splitter Hamiltonian between the two, and should entangle the two cats in the two cavities. Okay, it's more complicated for the 4-photon process. I'm not going to go through, but it seems like using some ideas based on JPC, so essentially some Josephson ring modulators, we should be able to fabricate the same kind of Hamiltonian with 4 photons, A for B dagger plus A dagger for B. And so this is also some project for future, probably for future experiments that we want to do, but so I'm not going to talk about that now. So okay, I'm going to finish here. I'm happy to answer any questions.
Any questions? Joe?
Yeah.
I had some difficulty identifying what of the operations were driven by pulses and what, if any, were driven by CW tones. And
Everything is CW here. There is no pulse. So okay, of course, yeah, of course, no. I'm sorry, no, of course. Well, okay, it is a pulse. Okay, no, you're right. So if you consider, for example, this, okay, everything till here to have this driven damped process is CW. So you just turn on CW pumps, and you have this. But of course, when you want to do a gate, you have to turn on this drive for a particular amount of time, which is given by exactly pi over omega. So you see, if you want to do for example, it depends on how much. What's the gate you want to do? If you want to do a pi rotation, it's just pi over 2 times omega x, where omega x is given by it's actually it's here 2 epsilon x square root of a number of photons.
Okay. So since I forget exactly where that slide appears in the sequence of things, so is it that all the all the parity syndrome measurements are done?
No. Okay, no. This is I've not talked about parity measurements here.
Right.
This is just operations. I'm saying that no, if I want to do so okay, I have first. Okay, so maybe I have to go to this slide of summary slide that I had in the.
Yeah.
Okay. So okay, this 2 photon or 4 photon process just brings me in this space of alpha minus alpha I alpha minus I alpha. It just make it tractable with respect to parity errors. I'm not. You need to add something on top of it to measure parity. I've not talked about this during this time. So we know that we have the possibility to do that. I've not talked about this here. So whatever I've talked about is just that assume that you have this, and I want to do no operations on my states. So these are CWs, of course, the decay operator and the driving Hamiltonian for my encoding essentially is CW drive. So they're always on to put the cat states there. And then if I want to do an arbitrary rotation of some angle theta around around the x-axis of my qubit, I turn on some drive for some time, which is depending on this theta, of course. And so it's not like in usual Rabi pulse. And okay. So of course, for the pi over 2 rotation around the z-axis, I have to turn off these CW tones, and then wait for some time. That's what's going to go on. 2-qubit entanglement gate these are turned on. These are again on. The CW tones are on, but you have a pulse of some particular length again. Perform some.
So for this summary, the protection is CW, and the operation, the gates are pulse.
Yeah.
Why do you use cat state for error correction? Because there is some more simple error correction code like boson code.
Well,
that is up to, for example, 4 photons. In the case of cat state, you have to use a lot of photons.
No, not
which
really.
Which means it is very weak for dissipation.
No, so that's what I'm saying. Actually, what I've shown here is just that you don't need that much photons. So that's everything that I've done here is just with 4 photons. I have all these simulations that I've shown.
But in principle, coherent state contains a lot of photons. It is very small probability, but you have to have infinite amount of photons.
But these are the states which are most easily prepared and which are most easily tractable with respect to the decay to the single photon channel. That much better than Fock states, for example, of course, because you see, I mean, actually, this is something which is, I find it quite nice. The cat states are the only states on which the photon loss operator, the A operator, can be seen actually as a unitary. That's the beauty of this.
Okay, that is because coherent state, eigenstate of.
Right. But it's especially just this. It's just that. If you look at the state alpha plus minus, if you are in these spaces of alpha plus minus alpha and alpha minus I, for example, for I alpha, plus minus I alpha, I mean the orthogonality is conserved by the application of the A operator. And so it's like a unitary. Whereas if you have, for example, I don't know, n and n plus 1, 2 Fock states, of course, you have the ratios which are different. You have a square root of n and square root of n plus 1. They become similar to a unitary only at the limit of very large n. That's the, I would say, the beauty of for this decay process, of course, for the A decay process, for the photon loss channel. I think these cat states are natural choices of logical qubit because the action of the photon loss channel is a unitary. Yeah.
So I was wondering if you investigated what is the stability of the prepared cat state with respect to preparation errors.
So here there is no preparation error anymore because that's what I'm saying. I have a set of gates here. So what I do is I start from vacuum. I turn on my pumpings, which brings me to first cat alpha plus cat minus alpha. Okay,
Right.
that's
What if you don't start from vacuum? That's right. If there is some initial residual coherence or
okay, so I'm saying that you can do initial preparation in this. So you have a reset which brings everything to vacuum. So that's easy to do. And then you just turn on the pumps, and this is you can bring very rapidly to the zero logical of your qubit. I mean, preparation of the zero logical is just a reset toward vacuum and turning on the CW drives, which brings you to the zero logical. And then you do this set of operations that I said to you, I showed, to prepare in any state that you're interested in. So this initial encoding can be done in.
but then it's fragile with respect to this initial. I mean, you need to start exactly with the vacuum, right?
So there are ways to measure the photon number with high fidelity. You can measure the photon number in the cavity with high fidelity using a qubit.
You can.
You can measure the photon number inside the
Yeah.
qubit using
So
photon number dependent qubit rotation. That can be done with a very good fidelity. That
Right.
give a measurement in measurement-based preparation of the states.
So you can, yeah, I mean, there are various schemes. Actually, Zeki has tried to use the same setup to cool down the high Q cavity through the low Q cavity. You can, for example, use the set of pumps, which just evacuates the photons inside the high Q cavity from the low Q, using the low Q cavity in the same parametric kind. So you can really bring it very rapidly to the vacuum state in this manner.
I think we're probably close to the question. Let's thank